some of you have asked me to record a few more videos because you asked these questions in the classroom, and I thought I would record one more video for momentum. So it will be momentum and energy involved in these videos. So let's look at some of the questions that I prepared for you. So here is the first question, and they say a bullet of mass 5 gram is fired into a block of mass 250 gram that is initially at rest at the edge of the table that this has height of 0.45 meters. The bullet remains in the block, and after the impact, the block lands 1.2 meters away from the bottom of the table, and you have to determine the initial velocity of the bullet. So at first I'm going to convert the masses for both the bullet and the block. So the mass of the bullet is 5 gram, which is 0.005 kilogram. And the mass of the block is 250 gram, which is 0.25 kilogram. And then they give you the height, which is 0.45 meters. And the distance where the block and the bullet land, which is 1.2 meters. So this is the information that is given. And always when I solve these problems, I'm gonna always write everything that is given, because that's the easiest way to start the problem, because next I'm gonna write the formulas that I know. So from here, what I know is the height of the table is given. Because the height of the table is given, I can use the dot formula to find the final velocity. So the final vertical velocity at the moment when the block and the bullet land I can use the distance and acceleration due to gravity. So that's the square root of 2 acceleration, the distance it travels vertically, and plus vertical initial velocity, which is 0. So if I plug in 0.45 for the height, I'm going to get 3 meters per second. So if my final velocity is 3 meters per second, I can figure out the time it took to hit the ground. So this time, the time is equal to change of the velocity, vertical, y, over the acceleration. So the final velocity is 3, and initial vertical velocity is 0, and acceleration is 10. So that gives me 0.3 seconds. So the block and the bullet will hit the ground in 0.3 seconds. And now if I want to calculate the initial horizontal velocity, I'm going to call this one Vx. I can use this distance to calculate the initial horizontal velocity. So Vx is equal to the distance it travels horizontally over the time it takes to hit the ground. The distance is 1.2 and the time is 0.3 seconds. So the velocity is 4 meters per second. Now, because there are some damages done when the bullet gets into the block and gets stuck in there, I cannot use kinetic energy before is equal to the kinetic energy after, but the momentum is always conserved. So I can say momentum before is equal to the momentum after. And so for the momentum before, I have the bullet times its velocity, initial velocity. So let's call this one initial velocity of the bullet, plus the mass of the block, momentum of the block, times its velocity is equal to, and they stick together, so it's m plus m, and their velocity after. And this velocity after is the one that we just found, so that is that Vx velocity. If I plug in my numbers, I'm gonna get the mass of the bullet, velocity of the bullet, and mass of the block times velocity 0 equals 0, and the masses of them after, which is 0.25, so 0.005 plus 0.25, and the velocity of both of them after is 4 meters per second. So I get the initial velocity of the bullet is equal to 0.255 times 4 divided by 0.005. And I can times the numerator and denominator by 1,000 to get rid of the decimal. and I get the velocity, initial velocity of the bullet is equal to 204 meters per second. In this question, and I don't think this is a very difficult question, but it was given on AP exam. So I thought sometimes students in my physics classes ask me for challenging questions because they were not allowed to go to AP physics class, and their next step is going to be AP physics class. So this is one of the easiest questions that I can show that AP physics students also look at. So the two slightly separated balls dropped from some height of 9.8 meters above the ground. So initial height of the balls is given, and that is, I'm gonna call it h. So h is given, and 9.8 meters above the ground. And they approach this surface with vertical velocity of v. So because the height is given, I can find the vertical velocity, which is the final velocity. I know the distance and I know acceleration, so I can use the Dow formula. So the final velocity is equal to the square root of 2, acceleration is 10, and the distance vertical is h, and initial velocity vertical is 0 squared. So if I plug in 9.8 into the formula, I get 196, and that one is to the power of 0.5 with the square root of it, will give me 14 meters per second. So the final velocity is 14 meters per second. That means the little one, the small ball, and the big one both hitting the ground at 14 meters per second. And then they say the ground observer sees the larger ball hit the bounce back at the same velocity as they reach the bottom. So that means this one is also coming up at the same final velocity. This is where I can use momentum before and momentum after. So this is your final velocity, and this one is bouncing back with the same final velocity. So for momentum before and after, I will have momentum before, I have mass of the little one times its velocity, v final, plus the mass of the second one times the same velocity equals 2. And then they say that after the collision, assuming perfectly elastic collision and the large ball has a mass is given, and calculate the height to which the small ball will go if an upward velocity of the big one after the collision is 0 meters per second. So the M1 will move with some velocity 1, but M2, the large one, will have 0 velocity after the collision. If I plug in the numbers, I will have mass of the first one is 0.5, and the velocity is approaching, it's downward, so it's negative, so I'm going to plug in negative 14, plus the mass of the second one is 2, and its velocity is upward at 14 meters per second, because they say it's exactly the same velocity as it reached the ground, equals to the mass of the first one is 0.5, and the velocity of the first one I'm looking for, the little one, plus the 0. And this is the velocity at which the little ball is going to be leaving after the collision. If I do my calculations, I'm going to get that v1, or the velocity of the small ball after the collision, is equal to 42 meters per second. And if I want to calculate how much higher it will go, so after the collision, the little ball is going to have the velocity of 42 meters per second. And only force that is acting on the little ball is going to be the acceleration due to gravity. So the ball is going to be losing its velocity. So the little one, after the collision, is going to go at the velocity of 42 meters per second. So the time it's going to take for that little ball to stop is change of its vertical velocity over acceleration. Its final velocity when it stops is 0, and initial is 42. and acceleration is deceleration, so it's -10. So that will give me 4.2 seconds before the little ball stops all the way at the top. And I want to calculate how much higher it will go. So if I want to calculate the height at which the little ball is gonna get or go to, that's gonna be its average velocity times the time. So its initial velocity is 42 meters per second, and its final is 0. So 0 plus 42 divided by 2, that's average velocity. And the time it's gonna take for it to go up is 4.2 seconds. So I get the answer as 88.2 meters. So both balls fell down from the height of 9.8 meters. So right there is 9.8 meters. But the little one, after the collision with the first one, if we assume that the larger one stops, so the little ones after it collides with the large one will go to the height of 88 meters after the collision. And I have a video of physics girl when she has 2 and 3 balls shooting like this down from certain height, and it shows in the video how high the little one will go. So in your conceptual videos, you have the physics girl video that she recorded, and I really like that video and you should watch it. So that was one of the AP exam questions that I also wanted to show to my regular physics students as well. Here is one more example that the students asked me to do in the classroom, so I decided I'm going to record it for you. You see there's going to be a collision, so every time you have a collision, you use momentum before equals to the momentum after, and in this case you have 2 objects before the collision, 2 objects after the collision. So we're going to do write the formula for momentum before is equal to the momentum after. So I have for before m1v1 plus m2v2, and I can say initial and initial, and after I have m1v1 plus m2v2, and now I'm going to plug in my numbers. So m1 is 1 kilogram moving at the velocity of 2 meters per second, and m2 is 2 kilogram moving at the velocity of -2 meters per second. Sometimes they will not tell you that it is -2 meters per second, but you can see it is in the opposite direction, so you have to remember to plug in a negative number. After the collision, you have m1 is 1 kilogram moving at the velocity of -1, so it changed the direction of the motion, so it moves in the opposite direction as well. And then you have m2, and you're looking for this velocity, and m2 is given 2 kilogram. So we have 2 minus 4 is equal to -1 plus 2v2. So from here I see that v2 is equal to -0.5 meters per second. So the mass 2 is still going to continue moving into the same direction as it was moving, in the negative direction, but its velocity is not 2 meters per second now as it used to be. It's going to be -0.5 meters per second. So every time you have a collision, you want to use conservation of momentum, because the momentum is always going to be conserved, and energy is only conserved when they state it is elastic collision. Or you can check whether it is elastic collision or not by calculating the energy before and after, and if the energy is conserved, then a collision was elastic. So for this problem, we have the same conservation of momentum. There's going to be collision, but in this case, mass 2 is not moving. So for before the collision, I have m1v1 sub 0 plus m2v2 sub 0, and I'm going to plug in the numbers. I have 1 times 2 plus 2 times 0. And then after the collision, I have them both stuck together. So instead of writing m1v1 plus m2v2, because they have the same velocity and their masses are combined, I could write as m1 plus m2, because they stuck together, instead of writing them separately and moving at the same velocity. So their masses combined gives me 3 kilogram, and I'm looking for their velocity after. So v is equal to 2/3 meters per second, or 0.67 meters per second. In this question, they don't give you the mass of the second card. So you have to figure out the mass of the second card, but they give you the velocity of both of them after. So for momentum before, neither one of them is moving. So I can write it's mass 1 plus m2 times the velocity of there is 0 because neither one of them is moving. And for the momentum after, I have mass with 2 kilograms moving at the velocity of -2. And this mass is not given, moving at the velocity of 0.5. So if I move this term to the other side, I'm going to have 4 is equal to 0.5 m2. And if I divide by 0.5 both sides, then m2 is equal to 8 kilograms. In this case, the frog is fallen down, and they give you that the frog's mass is 0.5 kilogram. So they give you the mass of the frog is 0.5 kilogram. And because the frog does not have the velocity horizontal, so it cannot add the momentum in horizontal motion, but it can make the whole system heavier. So if I do conservation of momentum before, I only have 1 kilogram mass moving at 3 meters per second. So mass times velocity before. And the frog has 0 forward velocity, so that's 0.5 times 0. Even though it has vertical velocity, it does not have horizontal velocity. And after the collision, or after the frog lands on the cart, their mass together combined is 1.5, and I'm looking for their velocity after. So I have 3 is equal to 1.5 v, and the velocity of both after is equal to 2 meters per second. And I'm gonna stop our video on momentum 3 for physics classroom at this point. I just wanted to do a few more questions that you guys had questions about, and a few advanced questions that you saw at the beginning with 2 balls falling down and with the block and the bullet. And thank you for watching, and I'll see you in the next video.